Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of campus recruitment data. So basically it's a bunch of students who are recruited on a campus, and at the end we have a salary column, and we're going to try to predict the salary that's offered to a given student or candidate based on a bunch of features for each candidate. So let's hop into the notebook. We're going to use a linear regression model with L2 regularization to make our predictions. So I'm importing NumPy and pandas just to work with the data, and we only need a few imports today. We're going to use the standard scalar from sklearn and the train test split function from sklearn for pre-processing. And then we will use the ridge regressor, or the it was an L2 regularization linear regression model. So I'm going to go ahead and import that, and then we can load in the data using pandas.readcsv. And we can get the file path over here. Just copy that. We'll paste it in, and we'll take a look. Alright, so we have 15 columns, and we have at least some null values here, and they happen to be in our target column. So when you have missing values in the target column, it's probably not a good idea to fill them in, because then you're basically predicting a value that was generated based on the existing values. So it's not a real value. Let's get a little info with data.info. And we can see it actually looks like that's the only column with missing values. There's 215 total entries, and the only one that has that doesn't have 215 non-nulls is the salary column with 148 non-nulls. We also have a decent number of object columns, so we're going to have to encode those as numeric data. Alright, so let's start pre-processing. And what I like to do for pre-processing is create a function, pre-process inputs, that's going to take in a data frame. First thing it'll do is create a copy of the data frame, and then at the end it will return the data frame. So that's how it will start, and then we'll add our pre-processing steps inside one by one and see how it affects the output. So let's return x, which will be pre-process inputs, and we'll pass in data. So at the top here, we have the original data here, and then the pre-processed data here. So anything we apply in the function, we can see the results. So let's deal with this last. Okay, because that's in the salary column, let's not deal with the missing values right away. I think the first thing I'd like to deal with here is actually the encoding. So yeah, let's encode these categorical columns. To encode them, we're probably going to need to figure out what kind of values are in each one. So a great way to do this is to create a dictionary that maps a column name to a list of values in each column. So for each column name, we're going to take x subcolumn, get the unique values, and then display it as a list. And that's going to be for every column in, I could do every column in x.columns, but then we'd also get all the numeric columns. So what we can do instead of x.columns, we can do x.select dtypes, pass in object, and then get the columns of that. So this will select only the columns that have an object data type. Now, just be careful that when you use this to visualize the categorical values, you have to make sure that you don't have any numeric values that are actually categorical. So when you select object as the data type, if let's say you have a feature that has some discrete numeric values but they actually represent categories, then you will miss them by using this, and you'll accidentally encode them just as regular continuous numeric features. So we'll take a look, and we can see the kinds of values that are in each categorical column. And so this is very helpful. We can now basically take a look and say, okay, are there any columns that have an ordering of values? Because if there's an ordering in a certain column, and there's more than two values, we can employ ordinal encoding. And if we have a column that has more than two values and does not take an order, we can do one-hot encoding. Additionally, if there is a column with only two values, then that can just be binary encoded, which means we'll set one of the values to 1 and the other to 0, and that's a very simple way. So looking at this, I don't see any ordinal features, right? It looks like we have a binary feature, another binary feature, another binary feature, and then all these three at the bottom are also binary features because they only have 2 values each. And these two in the middle, they have 3 values, but they don't take any order, right? They're sort of independent of each other. So we're going to one-hot encode these 2 columns and binary encode all the rest. So now that I know what kind of encoding I need, I'm going to write 2 functions, binary encode and one-hot encode. So both functions are going to take in a data frame and a column dict. The column dict will perform a different role in each function, but basically it's going to map. It's going to be a mapping. Let me do it for the binary encode first. So we'll start off by creating a copy of the data frame, and then I want to iterate through the column dictionary. So for column and positive value in column dict dot items. So what this is going to be, it's going to map a column to a positive value. And then we can iterate through those 2 at a time using the dot items, which will return the key value pairs as tuples. And the reason I want a positive value is I want to specify which of the 2 values is going to be the 1 and which of them is going to be the 0. So by specifying a positive value, we can choose which will be the 1, and the other one will by default just become the 0. So all we have to do to encode a column is take df sub column, right? That's the column we pass in, and we're going to rewrite it with a lambda function applied element-wise to every element in the column. A given element is given by x, and what we want to do to x is turn it into 1 if x equals positive value, and otherwise we'll turn it to 0. So this is all we have to do to binary encode, right? We pass in a column we want to encode and a positive value for one of the values in the column. This could be m, or it could be central, or it could be yes, or it could be one of these 2. It's sort of arbitrary which you pick. Yeah, so then if x is the positive value, we'll set it to 1, and otherwise we'll set it to 0. Then when we're all done, we'll return df. And the nice thing about this function is you can pass in a whole bunch of different columns you'd like to encode, and it's very useful, especially when you have a bunch of binary columns. Same now for one-hot encode. Is this going to be similar? We're going to start off by creating a copy of the data frame, and in the end we're going to return the data frame. So we want to apply some transformation to it, and I want to do it for every column in our column dict. So for column, and this time we're not passing positive values, we're going to pass prefixes. For a column prefix in column dict dot items. So the prefix is going to be the prefix that we put on our one-hot columns or dummy columns. So let's take an example. HSCS, I believe, that's one of our one-hot columns. Nominal features. So if we take that column, let's say x sub HSCS, that's just this column, right? Right. So if I call pandas.getDummies on the column, then each unique value in the column gets its own new column, and it gets one-hot encoded, which means we're going to have a vector of all zeros and a single 1. That's why it's one-hot, right? And the 1 represents the original value for that example. So over here we had commerce, science, arts. So the 1s go 1 in commerce, 1 in science, and 1 in arts, right? And you can see that's how it's been encoded. Now sometimes when doing this, it can get a bit confusing when you get these new column names. You're not sure where these columns came from. Maybe not so in this case, but if you have a lot of features and if you're one-hot encoding columns with duplicate values, then you might actually get duplicate column names. So it's a good practice to include a prefix here that will it'll append a little string to the beginning of each column name so you can remember where it came from. And so that's what we're going to do here. We're going to create some dummies using pandas.getDummies. except instead of just the HSCS column, we're going to do it for each column in our column dict, and we're going to specify the prefix as prefix that we're passing in here. That's going to be coming from our column dict. And then once we have the dummies, we're going to concatenate it to the end of our data frame. So we can use pandas.concat to concatenate the data frame, the original data frame, and the new dummies columns, and side by side, so axis 1. And that's going to be our new data frame, right? And then once we've done that, we can drop the original column from which we created the dummies, because we no longer need it. So df equals df.drop, column, axis 1. Alright, and that's it. This is our binary encode function and our one-hot encode function, and that should do the job. So now what's left is let's actually create our column dicts. So encode categorical features. I'm going to create a binary feature dict, and that's going to be mapping column names that are binary. So it's gender, SSCB, HSCB, work X, specialization, and status. Those are all the ones with 2 values. So I'll just copy them in, and well, we're going to want to also include the positive value for each one. So I'm going to pick M as positive value for gender, central as positive value for SSCB, central here for positive value of HSCB, yes for WorkX, market and finance for specialization, and placed for status. So I'm just going to copy that. I already wrote them before, so I'll just copy it in. And you can see I'm mapping here a column name to its corresponding positive value. Now we'll do the same thing for the nominal feature dict. And this is just the one-hot columns with the prefixes. So that's just 2. That's the HSCS and degree T. So we have HSCS, and that's going to map to a prefix. Let's call it HSC. And then degree T is our other one. And we can give it a prefix of DEG. Alright, and then all we have to do to encode is df equals binary encode. That's the function we have up here. And we pass in df and binary feature dict. Very similarly, we do it for the one-hot, except this is one-hot encoding. And instead of binary feature, it's nominal feature dict. Alright, we run that. Take a look. And we... Oh, sorry. Wait, what's going on here? It didn't seem to work. It looks like the binary encoding is working, but I'm not really getting the one-hot encoding. So let's see, something might be wrong. Column prefix, getting the dummies, concatenating the dummies, dropping the column. Alright, give me 1 sec, I'll figure it out. Alright, I figured out what the problem was. I had just forgotten to get the dummies for df subcolumn. I accidentally had just getting dummies for column name. Alright, so now it should work. Let's run that, take a look. Here we go, we have the one-hot columns on the end now, and the binary columns have been switched to 0s and 1s. Alright, so what's next on the agenda? Okay, let's deal with these missing values now in the salary column. So we could just drop them. That's certainly a solution. But we could be a little more creative. Why don't we save those examples, and we can make predictions on them afterwards based on the fit that we have from the rest of the data. So of course we won't have a way of verifying if they're good predictions or not. We can get some sense of that based on splitting a test set off of the data we do have. But it'd still be nice to sort of create those predictions. So why don't we do that? Here, let's split the missing salary data from the df, or from df, and save it for later. So to get that, all we have to do is find all the rows that have missing values in the salary column. So if we take x and type .isNA, we'll get a true-false data frame where a true value will only show up if there's a missing value in that location. So there's a missing value here and a missing value here, and that's why we only see trues here and here. Everything else is false. So if I sum this now over, for example, over axis 0 is the row axis. So if I sum over axis 0, it'll count up all the missing values in each row. In each column. But if I sum over axis 1, that will count up the missing values in each row. And this is more useful to us because now we can check for each example if there's a missing value count of over 0, so greater than 0, then we can get true or false values depending on the truth of the statement. So we have false, 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 and then true and true because there's a true and a true in these examples, right? So we can now use this true-false series as an index for x. So we'll index x on this true-false series, and we'll get back only the examples that have missing values in the salary column. So there's 67 rows with missing values, and this is basically all the data that we can't make. Well, we can make predictions for it, but we can't train the data on it because we have no label data. So why don't we use this as our missing salary data. So I'll call it missing salaries. And I'm just going to do the same thing I did here, but for df. So df indexed at df.isNA.sum over axis 1 is greater than 0. And so this will be basically this. Then after that, I would like to drop the salary column from missing salaries because there's nothing in that column. So missing salaries equals missing salaries.drop salary from axis 1. And then I'd also like to save the ID numbers. So this is an ID column. I haven't talked about it yet, but we're not going to need this column. It's not going to help us predict because it's a unique value in each one. However, when you're doing something like this and saving bits of data that you want to make predictions on, it's often a good idea to keep the IDs so that you remember which examples you're actually making the predictions for. So what I'll do is create a new series called Missing Salary IDs, and that's just going to be missing salaries sub SL_no, which is the ID column here, right? And we'll make a copy, and that will be, we'll just save that for later. And then we'll drop the missing salaries from the actual dataset because now we have them saved. We can now remove them from df. So missing salaries.index, we're dropping the indices, and that's from axis 0, which is the row axis. Anytime we drop rows, it's a good idea to reset the index, unless, like in this case, we wanted to save it for some reason. But I'm talking about this actual index over here. We want it still to be in ascending order and without skipping values, so I'm going to reset it with reset index, and we're just going to pass in drop equals true, which will ensure that the old indices, the out of order or the indices that are skipping values, are not added on as a new column. Okay, so that should do it. Let's run this. Oh, we have a problem. Oh, did I forget to close? What's the problem here? Invalid syntax. df.isNA.sum. Oh, I didn't put an axis value. This should be axis 1. Alright, so now just looking at x. Alright, so let's actually return df, but let's also return missing salaries. And we'll also return missing salary IDs. And now let's get those from here. Missing salaries, missing salary IDs. Alright, so here's our x. We no longer, let's see, we still have this, now all the salaries in here should be taken care of. If we look at x.isNA now, and if we sum over the axis 0, so if we sum over the rows, we'll get the total number of missing values in each column. And you can see we all have all zeros. And if you ever want to check the total number of missing values over the whole data frame, you can sum over axis 1 and axis 0 to get... what's wrong here? Oh, you actually don't have to specify. Then you'll get the total number of missing values in the whole data frame. Okay, so we have no missing values in our X, so this is looking pretty good. We also have this missing salary data, which looks like it's like X, but there's one less column because we dropped the salary column, right? And so this is all the data we have that doesn't have target values associated with it. We also have missing salary IDs, which is just the original IDs for missing salaries, which if you look, the SL number column is still on there, but we're about to drop that. So that's going to be the next thing we do, is drop SL no column. So like I said, this column is not going to help us make any predictions since they're all unique values. So df equals df.drop SL no from axis 1. And I also want to drop it from missing salaries. So missing salaries equals missing salaries.drop SL no from axis 1. Alright, now we just check that. Now you can see the SL number column is gone. Missing salaries no longer has it. But missing salary IDs should be the information for the missing salaries that we have now saved in its own variable. Alright. So I guess we're done pre-processing. Now we can just split and scale the data. So we're going to split df into x and y. So y will be what we're trying to predict. That's just going to be the salary column. And we'll make a copy. X will be everything except the salary column. So let's drop it and make a copy. Alright, and then we will perform a train test split. So we'll do this with the train test split function from sklearn, and that function will shuffle the data as well as split it. So train test split, pass in x and y, and a train size, so how much of the data do we want in the train set. We can do 80% since we don't have that much data, and we can include a random state, because like I said, this will shuffle the data. The random state will ensure that the shuffle always happens in the same way so that we can reproduce our results. That will return 4 values: xtrain, xtest, ytrain, and ytest. And so now we have a train set and a test set. And now let's scale. So scaling is very helpful especially for linear models like this. It basically gives each column it makes each column in X take on the same range of values. So right now we have very different ranges. For example, these columns only take on 0 or 1, whereas over here we have 270,000, 295,000, 400,000. Very different possible values in each column. The scaling will make it so each column has the same kind of values. So in this case we'll use a standard scaler. I did import that from sklearn. And this will give each column a mean of 0 and a variance of 1. There are other scalars you can use, such as a min-max scalar, which will take the min and the max and set the min to 0 and the max to 1, so that all the values are forced between 0 and 1. But standard scalar is pretty good for all-purpose scaling. Scalar.fit. So we're going to fit the scalar to the train set. So we're not fitting it to the test set, because in practice we wouldn't have access to the test set at the time of training. So this is sort of artificially produced test set, right? So we're going to fit to the train set, and then we're going to transform both the train set and the test set using the fit that we have just on the train set. So xtrain equals scalar.transform xtrain. And this will actually perform the scaling that will give each column a mean of 0 and univariance. So this is xtest, and we're going to transform it using the same fit to xtrain. And last, I want to scale the missing salary data as well, using the xtrain fit. Because this is more test data, we just don't have values for it, target values. Scalar.transform missing salaries. Okay. And now I want to return, instead of df, I'm going to return xtrain, xtest, ytrain, and ytest. Now let me just get those over here. So this function is returning 6 different values. And now we can take a look at one. Now this has actually been turned into a NumPy array because the scalar.transform function will do that. We can turn it back into a data frame like so, but we will lose the column names. So we can't see exactly the column names, but we can see that we have scaled each column to have a mean of 0 and a variance of 1. Okay, so I guess now we can train, because now our data is ready to go in. Missing salaries as well has been scaled. So now let's go into training and results. So for the model, we're going to use a ridge regressor. So ridge regression is just linear regression with L2 regularization built in. And we'll set an alpha, which is going to be the strength of our regularization. So regularization can help prevent overfitting. It basically forces the weights to not get too big. So it puts a limit on the weights by including the squared, it basically includes the squared values of the weights as something to minimize in the loss function. So it's not only minimizing the cost of how far off the prediction is, but it's also minimizing the size or the magnitude of the weights themselves. So I found that a alpha of 100 works best for this data. So we're going to fit the data to xtrain, ytrain, and then we're going to get an R2 score, which is given by model.score by default. Pass in xtest, ytest, and then we can print it out. Model R squared, and the R squared score is a measure of how dispersed the data is from our fit. So it's basically telling us how good our fit is. It typically takes on a range between 0 and 1, where 1 is the best, but it can go into the negative numbers, and it can get really bad. I must warn you, we do not have the best R squared score here, but you have to also take into account we only have 215 rows of data, and because we performed a train test split, we're actually only using 80% of those 215. So it's not a lot of data to train on. Alright, we're going to format and pass in model R2. And you can see 0.03 is our R squared score. And on a lot of other models, and if you can see, even if I just remove the regularization from here, we end up with a negative score. So this was the best I could find. I'm sure we can do better if we put our minds to it, but this will work. Now I want to also print out predictions for the missing salary values. So missing salaries, currently it's actually, these are examples with all the features we need to make predictions. So a model.predict can take in, for example, we pass an xtest, it will give us predictions for the salaries, right? So these are our predicted salaries, and the R squared score here is actually calculated off these predictions. The dot score function will make the predictions and then see how far off they are from ytest. So here, instead of predicting on xtest, I'm going to predict on missing salaries. And so now we actually have a bunch of potentially good guesses for the salaries of the missing examples. And you can see from this, they may not be the most perfect guesses, but they're not bad, probably. I mean, they're as good as we have. So this will be the missing salary predictions. And we can just print it out. Potential salaries for missing target values. And then I will print out, basically, actually I won't print it. I'm going to take the IDs, right, missing salary IDs, and that looks like this. And I want to concatenate that with the predictions. So I can do pandas.concat missing salary IDs and missing salary predictions. And I want to put them side by side, so axis 1 and predictions. And oh, okay, actually we have to turn it into a series. So this is returning a NumPy array, and to use pandas.concat it has to be a pandas series. So all we have to do is pd.series, and we give it a name, so salary. And here we go. We now have the, oh wait, we have a problem, and this is probably because we didn't reset the index on the salary IDs. So let's go back into our pre-processing function. So missing salary IDs. Before we copy it, let's reset the index, because the indexes have to line up if we're going to concatenate them. And we'll include drop equals true, again to prevent the old indices from becoming a new column. Now I'll get the new values. If we train this, it'll just be the same probably. And then running this, we now have the ID number and the predicted salary for that ID number. Alright, so that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.